Welcome to lecture number 12 for ECE 463 Modern Control, Full State Feedback. In today's lecture, we're going to talk about feedback, what it is, and why it's useful. In later lectures, we'll look at how to come up with feedback gains to stabilize systems. Now, with feedback, a system's dynamics determine how the system behaves. Feedback is a tool which allows you to change the dynamics of a system. For example, both walking and riding a bike are open loop unstable. Without feedback, you fall down. With practice, however, you eventually learn how to stand and walk. Walking is a big deal. Your parents remember your first step. With practice, you can learn how to ride a bike. And you probably remember first time you hopped on a bike, you tried riding it, you fell off, skinned your knees, very sad. Eventually learn how to ride your bike and stay upright. What you're doing is you're adjusting your weight, adjusting the steering based upon how you're leaning. You're applying a feedback mechanism to keep you upright. And to illustrate that, if you fall asleep or pass out, you fall off your bike. If you're standing and pass out, you fall over. Those are systems which are open loop unstable, but with feedback, they're stable. And feedback is all important. Many systems are open loop unstable, but with feedback, you're able to make them work. For example, in economics, boom and bust cycles have been noted all the way back to the time of the Romans. Typically, the economy goes up and down, up and down. You have these boom cycles, bust cycle, boom cycle, bust cycle. What happens is during good times, people have jobs, they buy more. As people buy more, companies sell more. When companies sell more, they have higher profits, hire more people, give pay raises. As people get more jobs, more money, they buy more, and you have this positive feedback loop. So the economy just takes off. Then suddenly, something happens. People quit buying. As people quit buying, the companies quit selling. As they quit selling, they lay off people. When people get laid off, they buy even less. Companies sell even less. They lay off even more people. Have this big crash. And eventually the economy picks up again, and you get a boom, then a crash, boom. This has been going on since the time of the Romans. Even in the Roman Empire, they noticed these boom and bust cycles. Feedback is what prevents that. The Federal Reserve is there to keep the economy growing at a nice constant 3% rate. And they do that by adjusting the money supply and the interest rates. The reason for 3% is if you grow too fast, you eventually get a crash. If you grow too slow, well, you could be growing faster. And they kind of found right around 2-3% growth rate is sustainable. Planetary weather is unstable. As the planet cools, you get more snow. Snow reflects more sunlight, cooling it off even further. As it gets even colder, you get even more snow. You have this positive feedback effect. When it gets cold, it gets colder and colder and colder. That can produce a runaway ice age, and that actually did happen about 600 million years ago. Warming is also unstable. As it starts warming up, the ice starts to melt, and you get exposed water. Water is 80% absorbent. Snow is 95% reflective. As more water gets exposed, that absorbs even more sunlight, which warms up the planet even further, which melts even more snow, and you have runaway warming. One thought as to what's keeping the planet from going through these boom and bust cycles is life. Life is providing the feedback to keep the planet from getting too wild. And you kind of see that in Earth's history. This is a plot of the temperature for the last 600 million years ago. About 600 million years ago was the ice ball Earth. Then when the ice melted, you get the Cambrian explosion, the dinosaurs ran around, the KT boundary, Permian explosion, right, or Permian extinction right here, then the age of the mammals. The last million years has been very wild in fluctuations in temperature, up until about the last 10,000 years. Then it's been very constant. One thought of why civilization took off 10,000 years ago is this right here. One thought is that you can't have civilization if you have wildly fluctuating weather. It took a nice constant period in Earth's history for cities to develop, for civilization to take off. That's one thought. Another thought is that dogs were domesticated 10,000 years ago. You can't have civilization without dogs. After all, the dogs protect your homestead. They protect your flock. They are needed to round up your animals if you have herds. It'd be very difficult to have a society without dogs. Might be coincidence, might be that's what caused civilization to take off 10,000 years ago. Just kind of a sidelight. Another example of unstable systems working with feedback, walking and crawling. Now with insects have 6 legs. The way the insects walk is they have at least 3 feet on the ground at any given time. 3 feet on the ground forms a tripod. That's open loop stable. And with the insect gaits, they'll either walk with 5 feet on the ground. As they go faster, they have 4 feet on the ground. Faster still, they have 3 feet on the ground. Insects never go faster than that. They always have 3 feet on the ground. They always have a tripod. That's open loop stable. You can only go so fast if you're crawling. Animals can do that too. When you crawl, you have 3 feet on the ground, your 2 hands, 2 feet. Only one of them is picked up at any given time. That way you've got a tripod, 3 feet on the ground is stable. You can only go so fast while crawling. If I want to go faster, I need to suddenly lift up my feet and have 2 feet on the ground. That produces a trot, a pace, or a gallop. There's also sometimes when you're airborne. That's when you're bounding. If you're willing to gallop or bound, you can go much, much faster. That's an evolutionary advantage, but that's unstable. If you can figure out how to stabilize a trot, pace, or gallop, you've got a huge advantage over a critter that's only crawling. So that's an example of sometimes that feedback are being used. Again, you see feedback all the time, but how does it work? There's a couple ways to do it. One approach is output feedback. This is kind of how the cruise control in your car works. I look at how fast the car is going and adjust the accelerator based upon the difference between the car's desired speed and its actual speed. The trick with output feedback is how large do you make this gain ky? Typically what happens is if the gain is too low, I get a very sluggish system. If the gain is too high, it starts oscillating. For example, when you first learn to drive a car, you jerk the steering wheel. That's the gain that's too high. If the gain is too high, you hit one curb, then you jerk the steering wheel the other way, you hit the other curb, jerk the steering wheel back, hit the other curb. You get this oscillatory behavior. Eventually you learn to back off on the gain and semi-gracefully go around corners. You can see that mathematically. If I have a dynamic system in state space, and I make the input a gain times my set point minus gain times the output, this is the closed loop system, A minus bky times c. As ky changes, the eigenvalues change. As the eigenvalues change, the behavior changes. If you want to know what is the optimal gain for y, that's a thing called root locus. That's what we cover in 461 control systems. I can see that mathematically. If I plot the roots of a minus bky times y, or a minus bkyc, for gains between 0 and 100, what I'll see is that when the gain is small, I start out at my open loop pole. This is the heat equation. I've got an open loop pole right around 0.4. As the gain increases, I speed up. Gain increases even further, I start to get overshoot. I start to oscillate. Then I go unstable. That's kind of what you saw when you learned to drive a car. If I jerk the steering wheel too hard, I go unstable and start oscillating. Back off on the gain, I can get a quick response without too much overshoot. And in 461 controls, we do a thing called root locus plots. This is your shopping list. It tells you all the responses that are possible based upon your feedback gain ky. The optimal gain depends upon your application. If I want a quick system with no overshoot, I'll design for this point right here. If I can tolerate a little bit of overshoot, I might design for this point or up here. Depending upon your requirements, I can define where I want to be, and then the feedback gain that I want is what gain puts you there. And that's kind of what we cover in 461 control systems. Again, with the feedback, I want high gains. High gains give you a quick response, better tracking, but I don't want too much overshoot. So suppose I were to say this is my desired pole location. That tells me the overshoot that I want. What gain puts you there? The approach used in 461 controls is at any point on the root locus, g times k is minus 1, find ky, and then set the DC gain to 1. What I wind up with is the following step response. The DC gain is 1, so I track the input. I get a little bit of overshoot. Depends upon the system. If I can tolerate, looks like about 55% overshoot, that looks okay. And the trade-off is a high gain gives you quick response. Too much gain gives me too much overshoot. So higher gain than what I used would give me more overshoot than I can tolerate, more than 55%. So again, that's kind of what we did back in 461 controls. A couple comments on output feedback. With only 1 degree of freedom, the closed loop poles follow a one-dimensional surface. That's the root locus plot. The root locus plot defines what responses are possible by adjusting your one gain, ky. If you want a better system, or you want to improve the response, then the trick is to add some dynamics to the feedback. I'll add a pre-filter, that's your compensator K of S. Sometimes I'll add a feed-forward controller, F of S. These are things that we cover in 461 control systems. A different approach, what we're going to be covering in this class, is full state feedback. Now here's the idea. If I have an nth order system, let's say A is 4th order, I've got 4 eigenvalues. I've got 4 states. If I were to feedback those 4 states, rather than the output, I would have 4 feedback gains to play with. With 4 degrees of freedom, I should be able to place 4 poles anywhere I want. It's basically 4 equations, 4 unknowns. If I can place them anywhere I want, I can sit there and specify where all 4 poles go. I'm no longer stuck on a one-dimensional surface like a root locus plot. I get any response I want. That gives me complete freedom, and again, likewise, I don't care. Is the open loop system stable, unstable, has to behave? I can do anything. That's the approach we'll be using in this class. Kx places all the poles of the closed loop system, and Kr fixes the DC gain. Usually makes the DC gain 1, so I track my set point. The problem, however, is how do I find Kx? What we did before is to find my gain Ky, I just let Ky sweep from 0 to 100, plot the resulting roots, and I get a nice one-dimensional surface. If I do the same thing here, I've got 4 gains to play with. If I just guess random numbers and plot them, I can take and put the poles pretty much anywhere I want. So that doesn't really help. I've got too many degrees of freedom. I need a better tool. A second way to find Kx. The eigenvalues of the closed loop system are A minus BKX. So here's my A matrix, there's my B matrix. I've got 4 gains. Pick these 4 gains to place the 4 poles. So when I do that, here's my new closed loop system, A minus BKX. The eigenvalues are the determinant of, or the roots to the determinant of Si minus A. So take Si, S times identity matrix, minus your A matrix. I get this. Now find the determinant. What you're going to get is a 4th order polynomial. That's a function of K1, K2, K3, K4. Pick those gains to put the roots where you want. This method really bogs down when you get past 2nd order. There really has to be a better way. And there is, so stay tuned, we'll be covering that. In order to do that, however, a system must be controllable. With full state feedback, you've got n equations, meaning n eigenvalues to place, with n degrees of freedom, your gains in kx. What we want to do is place all n eigenvalues anywhere I want. And the question then is, can you do it? Can I place all n eigenvalues anywhere I want? Or is there a solution for kx given the desired closed loop eigenvalues? And the answer is sometimes yes, sometimes no. To see when that happens, let's consider a couple cases. First, let's assume B corresponds to an eigenvector. Then if I do a change in variable, where T is the eigenvector matrix, I wind up in Jordan form. And my B matrix will just be 1, that's the eigenvector I'm exciting. Now let's do full state feedback. If I feedback the gains, I wind up with this for my closed loop system. This is upper triangular. A property of upper triangular matrices is the eigenvalues are the diagonal. So the one eigenvalue I can shift, the other 3 are fixed. If they're fixed, I can't put them anywhere I want. So this system doesn't work. And from before, if B is an eigenvector, it's not controllable. You can see that in MATLAB as well. If I take my A matrix, make B one of the eigenvectors, here's my closed loop poles. If I then apply a random set of feedback gains, close the feedback loop, 3 of the poles didn't shift. So those 3 poles are fixed. Only one of them did move. That's going to tell you the poles that are fixed are not controllable. Case number 2. Suppose B contains 3 eigenvectors. In that case, when I go to Jordan form, I'll have a diagonal matrix for A, kind of by definition of Jordan form. My B matrix will have 3 terms, since I have 3 eigenvectors. The fourth one will be 0. Now let's use full state feedback. In this case, that fourth mode is not going to shift. Again, it's not controllable. That kind of tells you that to be able to place the poles anywhere I want, B has to contain all 4 eigenvectors, which from the PBH test means the system has to be controllable. So that's the answer to the first question. When can I place the poles anywhere I want? And the answer is when the system is controllable. The second question is, okay, assume the system is controllable. How do I find the feedback gains? Well, that's a little bit harder. That'll be tomorrow's lecture. But in summary, feedback is all important. With feedback, you can take systems which are open loop unstable and make them stable. Stable is important. If it's unstable, you do things like you fall over, it blows up, stuff breaks. You got to be stable to be useful. Feedback allows you to improve the response of a system. Even if you're open loop stable, you can improve it with feedback. For example, a soldering iron. If you apply a fixed temperature at the base, it's going to take a long time for that heat to propagate down the bar. With feedback, I can crank up the heat, get it to warm up, and then drop it down, so I get a much quicker response time. It's what you do with your car. When the light turns green, you floor it, and then back off. That feedback improves the response of a car so that rather than very slowly getting up to 35 miles an hour, you can get there much quicker. Feedback also allows you to track a set point, such as your car. If you want to go 55 miles an hour, your cruise control can get you there. With a soldering iron, I set the tip temperature to 650 degrees. It'll get there. The following lectures will look at how do you determine the feedback gains to meet those requirements. So that's lecture number 12 for ECE 463 Monitoring Control. Feedback.